Hello, this is Jim Lochran from EarthShift Global, and welcome to our Brown Bag webinar. Today's webinar is titled Overcoming Barriers to Incorporating Uncertainty in LCA. Today's moderator will be our own Caroline Taylor, and we'll be fortunate enough to hear from Jeremy Gregory. Jeremy is a research scientist in the Department of Civil and Environmental Engineering, and he's also the executive director of the Concrete Sustainability Hub at MIT. Now, Jeremy's going to talk to us a bit about some of the barriers of incorporating uncertainty in LCA and provide some great examples of how he and his team are really overcoming some of those barriers. We recorded this session last week. Unfortunately, we missed the very beginning of the recording. So I'm going to step out now and hand it over to Caroline and Jeremy. Enjoy.
Characterizing uncertainty is difficult. And three, there's also this issue that people have a hard time processing outcomes of uncertainty analyses. So what I want to talk about right up front is basically, what might be some of the strategies for overcoming these barriers. When it comes to the first one, there's limited guidance on how to conduct an uncertainty analysis. We as a community can work to establish more detailed guidance, and Lisa Lauren from EarthShift Global is leading an effort within CTAC to try to do that, and some of us who are on this call are involved in that. So we're certainly trying to do that. I'm going to propose some of the ways that we think some guidance should be established. Number two, characterizing uncertainty is difficult. This is often something that we hear as well. So obviously we can develop more prescriptive uncertainty characterization guidance. I think we should also expand how uncertainty is incorporated into life cycle inventory databases. And then the last one that I'm going to talk a little bit more about is some ways that we can under-specify uncertainty. That is, not worry so much about exactly what the uncertainty should be, but rather be a bit more generic about it. And on the last one, this is obviously the most challenging one. People have a hard time processing outcomes of uncertainty analyses. I don't know if that means that everyone just needs to study statistics more, or rather, I don't think that's going to be a solution, but rather, I think we just probably need a bit more education about uncertainty, or at least have it embedded within analyses. So the structure for this talk is basically I'm going to talk about each one of these topics and probably spend the most time on this first one, basically that there's limited guidance on how to conduct an uncertainty analysis, and then also talk about some ways in which we might establish more detailed guidance. So the typical framework that you see for life cycle assessment, and this is going back 20 some years or so, is that basically for the two major components of a life cycle assessment, you have your life cycle inventory, and then you have your life cycle impact assessment. And people usually talk about parameter uncertainty, which is about the input, scenario uncertainty, which is about choices, and model uncertainty, which is about mathematical relationships. And while some of that is useful, as I'll talk about, it also can be difficult to sometimes tell them apart. And so we have some other ways to think about that. But generally, people do differentiate uncertainty in the life cycle inventory as opposed to in the life cycle impact assessment. So, but when it comes to conventional guidance on uncertainty analysis, this is literally it comes straight from the ISO 14044 standards. And basically, if we zoom in on this, what it says is, for any life cycle impact assessment that's intended to be used in comparative assertions, intended to be disclosed to the public, an analysis of results for sensitivity and uncertainty shall be conducted for these studies, basically. So on the one hand, I think that's good, but on the other hand, that's about all that it says. You should just do an uncertainty analysis. It doesn't really get into how you would do that. So that leaves a gap. Fortunately, some of the standards that have come afterwards have gone into this in a bit more detail. The PAS 2050 standard out of the UK also recommends a more formal uncertainty analysis should be done, but they don't really give much guidance on how you differentiate some of those different types. The greenhouse gas product standard, which came out in the early 2010s. Also has fortunately has a chapter on uncertainty and has separate guidance on it, even uncertainty tool. And basically what they say is that you should perform a parameter uncertainty analysis for a few scenarios. And that's kind of the example shown here, is that you have a baseline scenario and then a couple different scenarios, like maybe different types of electricity, and then the bars represent parameter uncertainty, so your uncertainty in the input. So while it's good that we see that, there are still several challenges to implementing uncertainty analyses. One, obviously, data collection in general for life cycle assessments is costly, and this seems to get larger when you're talking about uncertainty, although I'll talk about that's not necessarily the case. As I mentioned, sometimes it's difficult to distinguish between different types of uncertainty, this parameter versus scenario, and a lot of that is because even when we're talking about scenarios, everything really is manifested in the life cycle assessment in terms of parameters, and so but the way that you decide what those parameters are can often determine the type of uncertainty. Another thing that's a bit more subtle, but we've learned, is that information about decisions are lost when scenario uncertainty is interpreted like parameter uncertainty. And what that means is that basically, parameter uncertainty actually can be a combination of variation that's inherent in kind of any measured data, but it can also be associated with perhaps something about data quality, and so, but there are different ways that we end up treating that uncertainty, and the way that we characterize it, which is different than how we want to treat scenario uncertainty, which is more about the choices that we make. And so sometimes we group those together, we lose that sense of what's the implication of those specific choices as opposed to uncertainty associated with the parameters. So like I said, some of that inherent variation. The other trick is that, when you start talking about scenarios, which are basically choices that you're making about how you're framing the analysis, there are essentially infinite choices that you can make. And so that makes it a challenge to analyze the uncertainty associated with that. And as a consequence, because they're about decisions rather than like empirical data that we see, they shouldn't necessarily be averaged. You should be looking at them individually. So I'll get into a little bit about what that means. But like I said, these are all just different challenges that make it that are associated with implementing uncertainty analyses. So, all right, so let's talk a little bit about what are some of our guidance when it comes to conducting a comparative uncertainty analysis. The first thing is you want to define the types of uncertainty quantities that you're talking about. And the reason is because that then has implications on how you're going to characterize uncertainty for those quantities. Once you have that done, then you can conduct and interpret your uncertainty analysis. So let me go into each one of these and talk about what I mean. First, when it comes to the uncertainty quantities, excuse me, there's what we did is rather than following this parameter and scenario uncertainty, we actually looked in the literature, and there's a great book by Morgan and Henrian from 1990 that talks a lot about how to incorporate uncertainty into policy-related analyses. And they talk about different types of uncertainty quantities. One of them is empirical quantities, and these are things that are, at least in principle, can be measured and should have a true value, right? So how much electricity is consumed, what are our particulate emissions, like, and in theory, you should be able to measure those, and there is some true value. And we contrast that with what we call model domain parameters. And these define the scope of a system, and there's no true value. There's no perfect value. You're just, as a practitioner, you end up choosing what we think is an appropriate value. So examples of this are like temporal or geographic boundaries. And then lastly, there are value parameters. And these are represent something about analyst preferences. And once again, there's only an appropriate value. So examples of this are like discount rates or allocation factors. These are the things that obviously we struggle with because there is no true value. We're just looking at appropriate values. Now, the reason why there are some other quantities that they talk about as well in the book about it, like decision variables and outcome criteria, but these are mostly the ones that we're going to talk about. Now, the reason why they matter is because they influence the way that you characterize uncertainty. So, for example, for the empirical quantities, because in theory they have a true value, we can characterize uncertainty with these using a weighted probability distribution, like a normal or log normal distribution. And we can get this type of data either from direct measurements or estimates or even data quality estimates as well. But when it comes to model domain parameters, it's not appropriate to use a weighted probability distribution because there is no, it's not like it's more likely that you're going to have one geographic or temporal distribution. For example, instead what you do is look at a range of continuous or discrete values that all have equal likelihood, right? And because these are all about the analysis scope. And lastly, when it comes to value parameters, once again, these should also be analyzed with a range of continuous or discrete values that have an equal likelihood. And the way that you exactly quantify how you're going to characterize these things is going to be driven by the types of uncertainty, whether it's uncertainty associated about the measurement of it, or we also call application uncertainty, which is basically where if you're taking data from one source and applying it to others, then that can also determine how you're going to characterize that. And I'll save that for another discussion, or if there are questions, I have some backup slides on that. But suffice to say, the type of uncertainty quantity affects the way you're going to characterize that uncertainty. All right, and the third step is you're going to conduct and interpret uncertainty analyses. For most analyses, this means you're going to do Monte Carlo simulations, which is basically where you're going to look at a whole bunch of different simulations where you're changing the values of all those different uncertainty quantities. And although it doesn't have to be Monte Carlo analyses, there are other approaches you can use and some that don't even involve simulations. But generally what you get is some type of result like this where you have a cumulative probability of results. So for example, this one's actually showing a cost here, but we have two different alternatives, and there's a couple different metrics you can use to then analyze differences between them. This would be differences in the means, or we can also look at differences at the 90th percentile values. So that's one way to do it, but another approach is to actually try and look at what's the statistically significant difference between the alternatives as well. And generally what we use is called a comparison indicator, and this is basically where in each simulation we calculate either the ratio between the two values, or another way is just to do the differences. And really the reason that's important is because it accounts for a correlation between the two alternatives in each analysis. And then basically this beta value is looking at what's the probability that that you can basically say that one is better than the other. So that tells us how statistically, how much confidence we have in the results. So the approach that we recommend for conducting these comparative life cycle assessments is that basically for each life cycle impact assessment metric that you're interested in, and that's what Morgan and Henry would call it, an outcome criterion, you do what we call a probabilistic scenario-aware analysis. And what that means is we do basically a Monte Carlo analysis, but we also try to do a series where we're looking at different sets of scenarios. And I'll talk a little bit more about what that means. But essentially it means we're doing a series of Monte Carlo simulations for each individual set of scenarios. And then what we do is then after we have all those results together, we ask this question: can all scenarios be resolved? That means, can we say a across all the scenarios that one alternative clearly has a lower impact than the other. And if it does, then that's great. That means your analysis is complete. You can clearly say that one alternative is better than the other. However, that's rarely going to happen. So then we could ask and say, maybe there are some scenarios that we think are going to be of particular interest. We're looking at this particular region, or we have this particular assumption about user behavior or something like that. And if we can resolve those, that is, we can say that one clearly has a statistically significant lower impact than the others, then we're also done. But if that's not the case, then what we're going to do next is use an approach to try to identify what are the influential parameters that are really driving this. What's contributing most to this answer, and then if we can get better data on that, if we can refine it, then what we want to do is try and reduce the uncertainty associated with those parameters and do the analysis again, and basically do that until we get an answer where the analysis is complete. If we can't refine them, then basically your analysis is also complete and you're saying there's no statistically significant results of interest. So basically, like, these questions here I think are really important for a comparative life cycle assessment. You always want to be asking, when can we say that one is statistically significantly lower than the other? So because we've been working for the past several years with the Concrete Sustainability Hub, we've been doing some analyses of pavements, and I want to give you an example of this approach applied to pavements. And so when it comes to pavements, we use a functional unit of what we call a center lane mile over a 50-year analysis period. And we look at a couple different designs, and we look at everything from materials and construction to maintenance and end of life, and those are all about materials. We also look at elements that are related to basically how the pavement design and maintenance affects either the fuel consumption of the vehicles driving over them, and that's this pavement vehicle interaction. It turns out that like a rougher road means that there's more fuel consumption associated with the vehicles on it. The albedo has to do with the reflectivity of the pavements. Carbonation is how much CO2 is absorbed, and also the reflectivity affects the amount of lighting that's required on that pavement. So we have a couple different pavement designs here. We're going to be considering design A and design C, and these are some details about the particular design. It takes place in Missouri, which has a wet freeze climate. And we looked at a couple different maintenance and rehabilitation scenarios, which are important when you look at a 50-year analysis period. So, all right, so getting back to our process, the first thing we do is define our uncertainty quantities, right? And as you might imagine, there are many, many parameters that are what we would call empirical parameters, right? Remember, that is like, in principle, they have a true measurable value. What's the fuel efficiency of the cars driving over it? What will the traffic growth be like in the future? What's the thickness of the Portland cement concrete pavement, which is PCC? What's the thickness of the asphalt concrete pavement? How much energy is required to do milling, et cetera, okay? So those ones I think are what most of us consider to be, typical input parameters. However, there are some other things that we consider that are called model domain parameters. So the design life of the pavement is something that a pavement designer chooses. And they basically say, I want this to have a design life of 30 years. And that determines how I design it. But I can choose a longer analysis period, like say 50 years. And in which case, at the end of that 30-year design life, there would have to be a major rehabilitation. And so those are just choices that the practitioner makes. Similarly, some of the models that are associated with albedo or this pavement vehicle interaction, people may decide that they don't want to analyze those because either they don't have enough confidence in the model, there's too much uncertainty. So we can do the analysis either including albedo or excluding it, or including this PVI or excluding it. And so those are all choices you're making about the scope of the analysis. Lastly, there are a few value parameters. So one of them is basically how you do your allocation at the end of the pavement's life, and how you account for that salvage life. And then the other thing is, what are different maintenance strategies that you're going to pursue? And once again, these are just essentially choices that you're going to make. So I'm showing here, 12 different parameters, but there's a whole bunch more. We had 140 total. All the rest of them are empirical. But when I talk about developing scenarios, basically what we do is we characterize uncertainty in all the empirical parameters using probably approaches you would expect. But when we develop scenarios, we're going to specifically look at choices that are made in these model domain and value parameters. And that's going to influence exactly which kind of scenarios we want to analyze. And like I mentioned earlier, we want to look at those scenarios versus parameters. Scenarios versus kind of empirical parameters separately. So, all right, so going back to our approach, like I mentioned, what we did is a Monte Carlo analysis to conduct this probabilistic scenario-aware analysis. So we do, essentially, we look at one scenario where we vary all the empirical parameters, get a result for that. Then we change something about one of those model domain parameters or value parameters and change that, and then do the probabilistic analysis again, and then again for another scenario. So we keep doing that for a whole bunch of scenarios, and that's what we mean by the probabilistic scenario-aware analysis. So as you might expect, when we do that, we do not get a result that all the scenarios can be resolved. That is, across all those different scenarios, we can't clearly say that one alternative is better than the other. So we keep going. And then this question about can scenarios of interest be resolved, this ends up being a little bit trickier than you might expect to answer, because particularly when you're looking at so many scenarios, how do you analyze which ones you're going to be interested in? So we use this kind of grouping of statistical methods called categorization and regression trees. And what that means, and these are available in most statistical analysis software packages. And what we do is basically we look across its ways of grouping different scenarios according to their statistical significance, okay? So that beta was a value where we're saying what's the probability that one alternative has a lower impact than another. And what this says is that basically across every single scenario, about 75% we can say are lower. And generally when you're talking about analyses where you can confidently say one is lower than the other, you want that number to be 0.85, 0.9, 0.95. There's not really a best number, but it's higher than 0.75. So what we do, what we're showing here are basically ways that we've grouped these scenarios according to some of these model domain or value parameters. So for example, what we've done here is basically, it turns out these category and regression tree algorithms differentiate scenarios that either exclude albedo from the analysis or include. And then within exclude, they look at ones that have different design lives. And then within that, we look at ones that exclude roughness or include roughness. And this is all done by those algorithms. Now, what we're showing in green here are basically, these are scenarios but where we can clearly say that one alternative is better than the other. So anything in green here, and it turns out there's 32 scenarios here where we can say, for example, that one alternative is better than the other, and there's 41 total across all of these. So what this says is that basically if we choose a scenario where albedo is included, but the roughness is excluded from the analysis, then there are 32 scenarios where we can say one is better than the other. Whereas in some of these other ones here, we have to get a bit more specific. We have to look at it, including roughness, 50-year analysis period, choosing this particular maintenance rehabilitation scenario, and this blah, blah, blah. And so all these different things mean that for this very specific set of scenarios, we have a few where we can say one's better than the other. So what I'm going to do now is basically, the next step, as you may recall, is if that was kind of too many, we then identify what are our influential parameters. And we do that using a sensitivity analysis. And once again, there are different statistical methods that you can use. But what this shows is basically what's the contribution to variance in global warming potential, and here's all kinds of parameters. So notice some of them are what we considered model domain parameters, and some of them are actually empirical parameters. So we're going to pretend that we could get some better data, because these ones here are scope, right? So they're just about whether or not you're including albedo or you're including roughness. So that's important and that's useful to know. But these are what the evolution is of the roughness of the pavement over time is a more empirical parameter, and so is the impact factor for bitumen. So we're going to assume that we can get better data for that and we can refine it. Then we can run our analysis again, and what we get is we get better results. We get an aggregated number now that's 0.8 across all the scenarios, and we're able to identify many more scenarios where we can say they're statistically resolvable. So now, for example, if albedo is included, then we can say across all those different scenarios that one is better than the other. If it's excluded, then we have to get a bit more specific. So the kind of the bottom line is that we want to interpret these parameters and scenario uncertainty separately, but we want to look at them together. So that's perhaps maybe a bit more detailed than it needs to be, but this is one approach we're using to conduct uncertainty analyses. But the other topic that I mentioned, the second one, was that characterizing uncertainty is difficult, right? So the first two solutions there about developing more prescriptive uncertainty characterization guidance is definitely helpful, and we can work as a community to do that. Expanding uncertainty in life cycle inventory databases is important. But this last topic about under-specifying uncertainty is an idea that we have and have been working to test out. And let me tell you a little bit about it. It involves actually two elements. One we call structured under-specification, and the other is probabilistic triage. And the whole idea behind these is to be able to streamline life cycle assessments. And when I say streamline, I mean we make the process faster, but we maintain the effectiveness or the quality of the outcomes. We're not limiting the scope or anything like that. And the way that we do it is we use what we call surrogate data to roughly characterize all activities. So we call this low fidelity or high uncertainty. So you can just be very generic in the beginning. So let's say you have some kind of generic life cycle assessment here. We have a bunch of different activities associated with production and then use and then end of life. If we take all the inventory data that's associated with those activities, and that's what these circles are meant to represent, is that life cycle inventory data. And what we do is basically those then become part of what we call our bill of activities, right? This is all the data that can that's needed for the life cycle assessment, and we do that under specification, which is we're very generic about what those activities are. And then we do this approach then, what we call a probabilistic triage, where we then identify what are sets of interest. That is, basically, there will be several different data sets that we determine from the triage that can just be left generic and can be left under-specified. Whereas there will be some that will be of interest that we should further specify. And those ones are where we should spend our time. So the reason that you streamline this is because you don't spend a lot of time trying to collect data on all these right here, but rather you only focus your efforts on these ones right here. So this under-specification requires some type of taxonomy, or basically a way of organizing how you're going to under-specify the material. So let me give you an example of what I mean by this. Let's say we're going to talk about a car door, okay? What we have for this particular taxonomy is different levels of under-specification. So level one is our most generic. That is, we could just say, if we're going to under-specify what that material is, it's any kind of metal, right? A more specific category of that would be to actually differentiate metals from ferrous metals and non-ferrous metals, and we're going to say it's a ferrous metal. Then level three would be a more specific characterization of that would be it's steel as opposed to iron. And then level 4, we could say it's a type of steel sheet, and then level 5, we could actually specify a very specific type of steel that's used, okay? So this taxonomy allows you to specify the level of detail for that particular product or process depending on the information that you have available. Right? And so once again, if that at the beginning of the process you can be very under-specified and specify, just basically define things based at level 1. And the thing is, these level 1 will have uncertainty associated with all of these different impact assessment methods across all these different levels. And then the more specific you get, then the more you reduce that uncertainty. So let me tell you how this is applied. This is showing analysis of a product that has a whole bunch of different components, see 42 different components. And what we've done is for every single component, we've under-specified them and basically just defined what they are using that level 1 low fidelity analysis. So for every single one. Then we run our LCA including this uncertainty, and what we find is that basically there's one particular product here, and even only a few of them, basically these 11 components contribute over 75% of the total impact, in this case cumulative energy demand, across 90% of the trials. So what we found here is that basically if we just choose to resolve these, this is our set of interests, these 11 components at basically a more detailed level. For those 11 components, we then get really specific and define them at level 5, but leave all these other components under-specified. What we find is that basically when we do that analysis, here was that original low fidelity one. You can see we get a high level of uncertainty. If we did what we call a high fidelity one, where we defined everything at that level 5, we get a very low amount of uncertainty. Whereas if we do that where we took that set of interests and did a hybrid of, most of the components are left underspecified at level 5, and we just define level 1 right here. When we do that analysis, then we get almost the same result as the high fidelity. So as we said right here, we further specified 25% or so of the components and left all the rest underspecified. So this is a way of trying to streamline this. So some of the benefits are that we don't need detailed uncertainty characterization for the majority of the inventory data, right? Especially if we start out having everything underspecified and then use that triage to figure out what's important. It reduces the data collection efforts for bill of activities. So that's one approach that we think can be used to make this a bit easier. But once again, there are other ways that we can develop guidance to improve the characterization of uncertainty. All right, last topic here is the one that I mentioned that's probably a bit more philosophical or maybe more leans towards social science than life cycle assessment. But there is this big challenge that people have a hard time processing outcome of uncertainty analyses, right? And this, cartoon is obviously a joke, but there are times when people get uncertainty information, they don't need to process it, they think it adds more complications, so they don't want it. But on the other hand, I think that statistics are really increasingly used in the media, and we see this a lot. So for example, we get all sorts of probability when we get our weather forecasts. People may choose to use 40% of umbrellas when they see that, but this type of information is available. Anyone who follows sports know that there are all kinds of predictions that are made with statistical probabilities. And, gosh, we see this in politics all the time. I was impressed to see this on 538. They already have predictions over a year in advance of who's winning the race for Congress, and it's based on polls, and then they have all kinds of uncertainty associated with that. And obviously, these types of predictions have gone under the microscope given the predictions that happened with our last presidential election in this country. But these types of things are being used. People are thinking about that. I think that also we have an opportunity to report comparative metrics that have a statistical basis, but don't necessarily require training in statistics to interpret. So, for example, a common, if you're talking about like a deterministic analysis, generally that would be like what you would report comparing two alternatives would be the difference between two alternatives. But if we do a probabilistic analysis, we can also report 90th percentile values. I mentioned we can also talk about the frequency that alternative B is the lower impact than alternative A. And then we can also calculate a maximum statistically significant difference between the two alternatives. So we can report all these things without showing PDFs or CDFs, and we can tell people this is kind of how much confidence we have in the results without actually getting into those kinds of details. And so we actually have some examples of this. My colleagues Elsa and Randy that I mentioned, they were involved and still are involved in an effort to apply some of these techniques to electronics. And here's an example of a study they did with for a product made by Lenovo, and what it says in the fine print there, all estimates are uncertain. Lenovo reports 95th percentile of the carbon footprint estimate to reflect that uncertainty. So once again, they're just showing one number, but they say it's the 95th percentile. So they say for this product, that estimate has a mean of 315 kilograms and a standard deviation of 58 kilograms. So that's a way I think of, having that uncertainty analysis behind it, but also not, having to show too much details about it. So that certainly I think is one estimate that we can go to, but what I'd be glad to hear are other thoughts that you may have about this. So with that, I'll be glad to stop and answer any questions you may have or just hear your feedback. So thank you.
Thank you very much, Jeremy. That was very, very interesting. So before we kind of go to the larger group discussion, we do have a couple of more focused questions. The first one is you said you'd be happy to talk a little bit more about characterizing application uncertainty. Mm-hmm.
Sure. Yeah. I can talk about that. And I had some backup slides here. So at least this is how we think about a couple of the key different types of uncertainty in life cycle inventories, okay? So one of them is, and I referred to this a few times, but it is what we call measurement uncertainty, right? And so this is, I think, what a lot of people would call more technically variation. And for us, we think it's a little bit easier just to talk broadly about uncertainty, but this is really variation or stochastic error. So sometimes in a life cycle assessment, this could be due to geographic or temporal or even process variation, depending on how you've aggregated your inventory. So, and the way you can characterize this is using data on variation or even estimates from an expert panel, which is actually what's done in EcoEvent. But there's a couple different types of what we call application uncertainty, and that, as far as I can tell, was first proposed by Greg Norris. We've refined it a little bit to call it what we call inventory quantities application uncertainty and intermediate flows application uncertainty. But I'm going to talk about inventory quantities. This basically has to do with the pedigree of inventory data amounts. So what's the appropriateness of input and output amounts from particular data source and how it's been applied to an inventory. So for example, let's say you open up a life cycle inventory for making steel, and it shows that there's 11 kilowatt hours of electricity that's required. Now, what this inventory quantities application uncertainty has to do with is what was the source of that 11 kilowatt hours. Believe it or not, when people don't have data for a value like that, sometimes what they do is they take a value from something else that's like a proxy or relevant. So that may be they either take it from a different region or a different time or even a totally different process. So that's the application uncertainty. And at least right now, the way that that's generally dealt with is the pedigree matrix approach is applied in EcoEvent. So that has to do with that 11 kilowatt hours. But there's also what we call intermediate flows application uncertainty. And so this applies to basically unit processes where you're looking at how appropriate is that particular intermediate flow to the particular application. And that intermediate, so for example, if I said 11 kilowatt hours of electricity, but that electricity is for a particular grid. And let's say that you're looking at steel making in Kenya, but you only have data on electricity from Egypt. You might apply that electricity from Egypt to this process in Kenya, right? So there's some uncertainty associated with that switch, or, sorry, not that switch, but basically that application of that data as well. And so what we have proposed, and others as well, have basically approached extending that pedigree matrix. And that pedigree matrix approach basically takes qualitative assessments of data pedigree or quality, and then quantifying uncertainty associated with that. So, so these are all different ways that you can characterize or quantify what's the uncertainty in data depending on the type of uncertainty. There's a couple others people have talked about, which is cutoff uncertainty, and of course there's always human error uncertainty, and these ones are just a bit more difficult to quantify. So, actually, I even had a good figure in here. This was kind of what I was talking about. How if you see something, for example, in that, then you know, there's the inventory quantities application uncertainty deals with the quantity, and the intermediate flows application uncertainty deals with the intermediate flows.
Thank you. That's very helpful. I had a question actually on the statistical nature of scenarios. You made the comment that scenarios are not statistical in nature and should not be averaged. How does that functionally work out from the end user perspective? Is that communicatable?
Yeah. What it usually means is that the fact that we're actually delineating something as a scenario is because I mean, sometimes it can be you just want to highlight that particular issue by itself and look at that particular influence, but usually it's because there isn't a way that we can say that one scenario is more likely than another. And that's what I mean by statistical in nature. So for example, you know, if we're looking at issues related to a scope, and that can be about what time period is the analysis, or what's the location, or maybe it could be even something around what type of data set. You have to kind of analyze each of those independently. And you can certainly compare the results from different scenarios, but as opposed to analyzing them statistically would mean, for example, that you would put them in your Monte Carlo analysis and give them a weighted probability distribution and just say, you know, here's how likely this activity is over the other. And so, like I said, I'm not really sure if that particularly answers it, but it's just that because we don't know what the likelihood is of one scenario over another, then we have to analyze them independently.
Sure. Do you find that in interacting with non-practitioners or non-researchers and non-experts that they're comfortable with that distinction? Do they recognize that distinction at all?
Probably not. No. I think that people use scenarios all the time, but what they may or may not recognize is like how explicitly that's actually tied to the choices that they're making in the analysis. And I think what it probably has to do with, I was going to go back, it has to do with this distinction between the empirical quantities and the model domain versus the value parameters. Whereas, we feel more comfortable in characterizing the uncertainty associated with empirical parameters, assuming we have the data, whereas quantifying that uncertainty with model domain or value parameters is more challenging. And that's why we want to make analyses of those a bit more explicit.
Okay, great. Thank you. I have a couple of questions kind of on the under-specification approach. Mm-hmm. I think the first is how broadly have you guys tested the under-specification method?
Um, uh, Gosh, I guess in the grand scheme of things, not very much, but it's been the work that I first showed, like about the door, was work that was done probably about 5-ish years ago, and that's actually this publication that's shown down here, and that was pretty generic. We applied it to a bunch of different products. More recently, though, we've been applying it specifically to buildings, and so we have quite a bit of work associated with that. I mentioned some of the work we've done with electronics. So I'd say we've done quite a bit when it comes to electronics and buildings, but beyond that, not very much. And the thing that I actually didn't really get into that much was this, this, how you decide what goes into level 1, level 2, level 3, how you organize those, is this taxonomy. And we also had a student look at different ways of organizing that taxonomy, which is still kind of an open research question for us, and one we'd like to study a bit further using different types of material. Because essentially, whether they've done it explicitly or not, for example, EcoInvent has a taxonomy for how they organize different life cycle inventories. And so that is one that you can use. But the implication when you do under specification, like I mentioned, so for example, when you do this level 3, quantifying the uncertainty at level 3 means that basically you're calculating the uncertainty across all of these different impacts, all of these different life cycle inventories. And as you can see just in this, these are real numbers right here of cumulative energy demand. So you can see it ranges from 25 to 0.7, right? So when it comes to developing the taxonomy, what we're trying to figure out is what does it mean to have things grouped together? You could say that maybe, obviously functionally, these are all quite similar, but iron scrap clearly has a whole different level of environmental impact. So it might mean that you should actually have a separate level 3 category that's just associated with scrap because the impact is so different. So that's, like I said, another research question that's of interest for us is how you develop those taxonomies. You could do it for all kinds of reasons. When we do the buildings, we've done it we've developed taxonomies according with how the buildings industry groups different materials together using the master format specification. But we've had students look at ways of perhaps doing it compared to cost or density. And so, like I said, that's kind of an open question for us.
Sure. Actually, it dovetails quite nicely into the next question, which is it possible or are they already implemented to use characterization and regression trees with some of the existing packages like CIMA-Pro?
So not in life cycle assessment packages.
Right.
Like for us to use the category and regression trees, we did that in a statistical software package. I'm pretty sure it was JMP. But the good thing is that you can do the analyses using something like CIMA-Pro and then kind of export the results into JMP, and then they can then analyze the results using those categorization and regression trees.
Sure. And then I think a nice springboard from that is, can design of experiments techniques be applied to compare a large set of scenarios?
That's interesting. When I think of design of experiments, I think of like the way that you would actually be structuring how you analyze the scenarios. So for example, the way that we organized our scenarios in this particular case is that basically we would specify a couple different values for design life, for analysis period, for each of these. And actually we had to keep it kind of limited because, as you can imagine, your scenario space expands pretty quickly the more alternatives you have for these values. So if you wanted to look at a lot of different model domain parameters and value parameters for a particular analysis, and each one had multiple parameters, that's what I mean where the scenario space expands rather rapidly. So that's where I think design of experiment techniques could be used to help you analyze. Maybe I don't need to analyze every single one of those scenarios, but rather I'm just going to analyze this strategic set of them, and I'm going to determine that using design of experiments.
Great. Thank you. I think we've got just a couple of minutes left for discussion. I want to take a quick opportunity. We have Peter Fatke with us today from TU Denmark, who's on the UNEP CTEC uncertainty group talking about guidance, which is very, very complimentary. So I was going to ask Peter to say something really briefly about the group and then use that to give us an opportunity maybe to chat about some of the guidance issues that impact both sides.
Yeah.
So Peter, would you mind?
Yes, thank you. Can you hear me?
Yes, we can.
Yeah.
Great. Thanks, Caroline, and thanks, Jeremy, for that excellent presentation. I was really looking forward to see that. I have read some of your publications in 13 and 16 that you have published, also in ESNT, and I was following that a little bit already. That is really great. Under UNEP CTEC, there is a big flagship project over several years in different phases. It's called Global Guidance and Harmonization of Life Cycle Impact Assessment Indicators, and we are already in a quite advanced phase. And uncertainty is, of course, one of the cross-cutting issues here that has turned out to really to be addressed separately in a small group. And we have different practitioners and model developers and other people in that group, and we are trying to, of course, with joint forces to come up with a kind of a guidance. And we have split that into guidance for practitioners, guidance for developers, and the general roadmap how to address, identify, and overcome all the challenges of which some of you have really discussed in more detail in the presentation today here. For example, how to do it in an inventory phase, how to address stochastic effects a bit more, how to interpret that and communicate that properly without running into trouble and actually understanding results and stuff like that. There are more challenges that we have identified, and I would be really happy to link up with you, Jeremy, and your group to see that we really identify synergies and how we can move that forward. In our group under UNEP CTEC, we are more descriptive in that way and listing what is out there, how can it be addressed. We have focused primarily on the impact assessment side, which I have seen you have not covered today in your talk here so much.
That's true.
Which is great because it's even more complementary then. And what we are doing is we really want to see to give an overview of where are the challenges and what needs to be done to address them. We are not in the task force so much in addressing them ourselves and developing the methods within the UNEP CTEC project, but of course that should state a roadmap where the research challenges are, some of which you partly already addressed today, but there are many more, and it will take more time and more effort. And then in separate projects, like in a collaborative effort, for example, with you guys, we could then link up and see how we address specific challenges that we have highlighted should be urgent or are making a big deal in the total uncertainty assessment and communication part.
Great, that sounds excellent.
Yeah. Our timeline is roughly, we have a big workshop where many invited practitioners, so UNEP has a process for that and selects people who should be invited to a big workshop that's called the Pulse workshop on the CTEC and UNEP, and we have that next June in 2018. And before that, we would be really happy if we can come up with something like a white paper addressing some of the issues that I just talked about, and if I could include you here in the process, it would be really great.
That's excellent.
And I encourage people, a lot of the materials will be available on the UNEP CTEC site, right?
Right, yes.
Right. I encourage people to take a look at those. In our last moment, one of the things that I think comes off of that is something for all of us to think about is, are there additional barriers to incorporating uncertainty that we maybe haven't included? Jeremy, do you have any comments on how kind of inclusive your perspective is?
Yeah, one of the things that, like I mentioned, that Lisa Lauren is chairing a group within CTAC North America about basically an uncertainty LCA roadmap. And actually, for those of you going to the LCA conference in a few weeks in Portsmouth, New Hampshire, I'll be chairing a session that's specifically on that topic. We have a couple speakers who will be talking about their thoughts on what are some of the barriers, and we're really going to try and keep it on this level of, like a practitioner level as opposed to more of a researcher level on that exact topic. So for now at least, that's a really good way to engage or also to contact Lisa about getting on the CTAC road mapping panel, because that was exactly, Peter, what I was going to say is that I think what's going to come out of that is supposed to be a document that kind of highlights, what the roadmap is that we see for trying to address uncertainty more in LCA. So I think that'll be a good contribution to your effort.
Perfect. Thanks, Jeremy.
Yeah.
Thank you very much. That's been a very interesting discussion. We are at the end of our time. I do want to take a quick moment to thank Jeremy for a very, very interesting seminar, and I think Peter for some good comments that help us realize really how significantly important this is for all of us right now. I also want to remind you guys that our next webinar will be October 26th. We will be on a bit of a panel around the CTAC LCA capability roadmap, which will also deal with uncertainty and some of the other issues associated with there. And we'll hope to see you all then. Everyone have a great rest of your Thursday.
Great. Thank you.
Thanks.